It's called direct air capture, or DAC for short, and it's a technology that takes excess CO2 back out of the air around us. The captured CO2 is then sequestered deep underground, or it can be used in other products. Today, you're going to hear some amazing things about direct air capture. You're going to hear about a CO2 absorbing nanomaterial that has so much surface area that just 1 teaspoon of it has the same surface area as a football field. As well, and I think this is a fantastic prospect, you're going to hear how direct air capture could become a major international industry for Australia, just like green steel, green ammonia and green hydrogen, with emitters in countries like Japan and Korea signing up to have CO2 taken back out of the atmosphere in Australia on their behalf. Welcome to Track Changes. I'm Murray Griffin of communications consultancy Earth. And today I'm going to be talking to 2 leading direct air capture experts, Julian Turecek, Chief Executive of direct air company AspiraDAC, and Professor Deanna D'Alessandro, Director of Sydney University's Net Zero Institute. Before we go to my chat with Julian and Deanna, a bit more about direct air capture. Firstly, although direct air capture systems all aim to do the same thing, there are 2 main types of DAC technologies. One type puts the CO2 in contact with liquid solvents to separate it out of the air, and the other type puts the CO2 in contact with a solid sorbent. Deanna has focused her research on solid sorbents, and as you'll hear, she has come up with the nanomaterial with the amazing surface area that I mentioned earlier. As for why we need direct air capture and other types of carbon removal technologies, think about this. It's not enough just to stop most greenhouse gas emissions actually being emitted. There will still be some left, and this residual CO2 needs to be balanced out. And to have a safe climate, we actually need to remove billions of tons of excess carbon dioxide from the atmosphere. Direct air capture is one way to do it. If you're thinking this all sounds ridiculously expensive, well, no one is pretending it's cheap. But it wasn't all that long ago that solar power was very expensive. And solar costs have plummeted as we've got better at designing and producing PV panels. And experts like Julian and Deanna are confident the same thing will happen with direct air capture. If you're wondering what an AspiraDAC plant looks like, well, they're modular, portable and solar powered. So think of a structure with a roof like a traditional house roof, or a tent which is covered in solar panels. And under that roof are a series of canisters that contain the nano sponge sorbent. Fans draw air into the tent where it flows over the sorbent coated surfaces. The CO2 molecules are captured while other gases just pass through. The sorbents are then heated until they release a very pure stream of CO2, which is captured and compressed, ready for injection into geological formations. And if you want to find out more about direct air capture or AspiraDAC or the Net Zero Institute, I've dropped some links into the show notes, including to the Direct Air Capture Coalition, which is hosting a conference in New York this month. Finally, before we go on to the chat, I'm just going to explain a few bits of jargon that crop up once or twice and explain a few names. Firstly, you'll hear a reference to the Frontier Buying Group, which has pre-purchased carbon offsets from various carbon removal projects, including AspiraDAC and several other direct air capture projects. Frontier represents some big names, including Alphabet, Meta, Stripe, and Shopify, and it aims to buy $1 billion worth of permanent carbon removal by 2030. You'll also hear a reference to Climeworks, which is a European-based direct air capture company that has 2 large direct air capture plants in Iceland and ambitions for many others. Another name that crops up is carbon engineering, which a year or so back was acquired by Occidental Petroleum. In conjunction with BlackRock, Occidental's carbon engineering is building the world's largest direct air capture plant in Texas. The plant, known as Stratos, will remove and store up to 500,000 tonnes of CO2 each year, and it's expected to be operational this year. You'll also hear a reference in this episode to ACCUs, which are Australian carbon credit units. Okay, that's enough intro. Let's kick off the chat. So, hello, Julian and Deanna. Thanks very much for joining us on Track Changes.
Great to be here, Murray. Thanks for the opportunity.
Likewise. Thanks, Murray.
First up, could you each give me a brief summary of your career so far and tell me what's been the career highlight, the thing that you're most proud of in your working life so far? So maybe, Deanna, I'll start with you on that one.
Yeah, of course. So look, I trained as a chemist, as a scientist at James Cook University. I'm a North Queenslander and grew up in Cairns in far north Queensland. After I did my Bachelor of Science and PhD, which I finished in chemistry, around about 2005, I moved to the United States, and I was there as a postdoc at the University of California, Berkeley for about 3 years. And it was there that I started working in the area of carbon capture and working on porous materials for carbon capture. So after that time in the States, I came back to Sydney, and I settled here in my starting out in a role as a lecturer, and then moving up through to become a professor. And I'm now a professor of chemistry and director of the Net Zero Institute here at the University of Sydney.
What's been the highlight for you so far?
I think the highlight is probably what I'm doing now. And the reason is that all the way through my career, I'm a very passionate scientist and feel very driven by the purpose of the sort of science that we're working on and the knowledge and the solutions we're generating. But it has become apparent over the last 20 years of working in the area of sort of clean energy and technology that unfortunately science and engineering can't solve these problems alone. And so the institute that I now have the opportunity to be a part of and lead with nearly 200 colleagues across this university, with many external stakeholders across industry and government and community here in Australia and abroad. What we do is really look at the holistic solutions. So we bring together the sciences and engineering and STEM areas with financing, policy, law, community experts, social scientists, to look at a more sort of systems level approach, because we know that no one of us can solve this alone. And I think that's been a really proud achievement. And I'm very honoured to work with such incredible people who have very diverse perspectives.
That's wonderful, Deanna. And I'm very glad you said the Net Zero Institute, because I must say, from the very little that I know about it, it just seems like a fantastic entity that's doing some great work. Yeah, so no wonder that you've chosen that as a highlight. Julian, over to you.
Yeah, so my background is engineering commerce from Melbourne Uni, and then an applied finance master's about 10 years later. So we're going back 30 years to my undergrad. And most of that time I've actually spent in the energy industry. So starting off as an electricity trader, gas trader, when the national electricity market was first started, all the way through to running power stations in the later years, and actually building new power stations as well. So I've operated in pretty much the whole gamut, the whole rainbow of colours, from brown coal to black coal to gas to pumped hydro, solar, wind, geothermal. Have had quite a bit of time in each of the technologies. But I've also been spending a bit of time in startup world and helping to grow a company called Corporate Carbon from when it was 3 people in a garage to being now one of the largest carbon project developers in Australia. So what I enjoy, the key highlights for me are building new things, imagining what could be that isn't already here, and then going from thought bubble to electrons into the grid, or thought bubbling to a new carbon removal project. All of the conceptual work on that, the economic work, and just bringing together the technical side of things and the commercial side of things. So yeah, the career highlights actually doing that, bringing a fast start gas turbine on in South Australia, and I truly believe that gas is a really good partner to help renewables come to the grid in scale. And more recently, building corporate carbon, and now I'm sure we'll be talking about it quite a bit, a new direct air capture technology.
And that is another amazing career, Julian. So thanks very much for that. Although, given that corporate carbon specializes in nature-based carbon, I would have thought it started out as 3 guys in a paddock rather than 3 guys in a garage. But I will, I'll take that as being a bit of poetic license. The garage bit, is that correct?
Oh, it's more of we probably don't have time on this podcast. It could be a podcast in and of itself, but it actually started really as a consulting company. But then as the carbon market started developing and the emission reduction fund came into place, corporate carbon's always been trying to figure out what's next and what are the innovations to happen in the carbon market. And so nature-based solutions and building carbon projects into the emission reduction fund was something that was a new business model about 10 years ago, but corporate carbon was one of the pioneers of that business, and writing some of the first methodologies to create carbon credits.
Yes.
But yes, it was literally 3 guys upstairs. Okay, it wasn't a garage. It was the founder's attic study, but same kind of idea.
Yes, absolutely. So now let's turn to the topic to hand. You both work on direct air capture, but in very different sorts of roles, coming at it from very different angles. So could you each tell me a bit about your respective involvement in direct air capture? And maybe Deanna, I'll start with you again.
Yeah, so our as a chemistry group, we're materials scientists, and so our role in direct air capture has really been around helping to design the materials as well as synthesize the materials and then characterize the materials. And over the last 6 years, as we've had the opportunity to be involved with great companies like Southern Green Gas and AspiraDAC and more recently DAC Labs, we've also ventured a little more to the engineering side and have been learning a lot along the way, and working very closely with the process engineers to interface these materials with the engineered systems. And that kind of is very, very easy to say, but in practice it has been perhaps almost, I'd admit, one of the greatest challenges of my career, because at the lab scale and at the lab bench, we have the techniques. We're the experts in how to design and make and characterize materials. But as soon as you take these materials and you want to actually put them in a real world environment, it's really not quite that easy.
Yeah, I can imagine it would be incredibly challenging. Julian, over to you. Can you talk about your involvement in direct air capture?
Yeah, so my role is leading a company that Deanna mentioned called AspiraDAC, and we're pioneering solar-powered direct air capture in Australia. So we were actually funded partially by a government grant from the Australian government a few years ago to create what would be Australia's first carbon removal project using direct air capture. And so it's been in a journey of putting together a project very similar in some ways, analogous to putting together a renewable energy project, finding the site, finding where we'd store the carbon once we've captured it, and actually focusing on, as Deanna said, the scale up from lab results to an actual industrial sized machine or set of machines to actually do the capture job. And the capture part is the hard part of it, where we're grappling with the thermodynamics of it. It does use energy, so making sure that it's using the least amount of energy possible. There's a whole range of different technical challenges to make it work. So it's quite a technically challenging set of activities.
So maybe just to follow up there, could you give me a bit of a state of play report on your efforts to prove up and commercialize the technology? Where are things up to now, and what are the next few steps?
Yeah, so we've actually built a prototype, and we're using some of the sorbents that Deanna has and her team have developed at the University of Sydney. We've characterized other sorbents that we've pre-qualified from other research activities from around the world, and we are now cycling those materials that we can talk about it more a bit later, metal organic frameworks, in our prototype here in Sydney. We're still doing some more work to go to optimize that energy equation that I mentioned earlier. And at the moment, we're using mains power, but we want to transition to use solar power. So we've still got a little bit of work to go on the technology side. But once we've done that, we've got the plans for the site and where we'll capture it. And so mainly it's at this moment, a technological prototyping, and then defining how we go to mass production after that.
You used the word sorbent. That's how the CO2 is absorbed. Is that correct?
That's correct. So there's a few different ways of doing direct air capture. We and the university have been focusing on using solid sorbents, which take up CO2 when ambient air is passed over it, and then release that CO2 when they're heated and under a vacuum. And the vacuum is essentially to separate out the atmosphere so that you're then just collecting CO2 molecules.
Okay, and I will turn now to you, Deanna, because that phrase, I think, metal organic framework, I came across in the prep for this, and I sort of have no idea what it means, but I'm assuming it's a type of sorbent or solid sorbent that has certain advantages from your perspective. For the layperson, could you tell us what a metal organic framework is and what those advantages potentially are?
Yeah, well, I think your description was excellent already, Murray. So,
oh, good.
So look, it's a porous material, and as the name suggests, it's made up of metal ions and organic ligands, if you like. And the organic ligands are a little bit like bridges that bridge between the metal ions, and they connect the metal ions into a three-dimensional scaffold, if you like, a little bit like a new building where you see the framework being put up. That's exactly what it is. It's basically a framework. And within that framework, it's porous, so there are lots of holes, and those holes are where you can store or separate or do catalysis and any number of other really interesting molecular functions within the material itself. So the real unique value proposition when it comes to materials like metal organic frameworks compared with, say, traditional sorbents, I should say, like zeolites or aluminosilicates that are used for, traditional applications in industry like petrochemical cracking and the like, is that metal organic frameworks have extraordinarily high surface areas. So we're talking about porosity here on the nanoscale. And so, each one of the little holes or pores in one of these materials is, 1,000th, even smaller than a human hair. And as a result, the materials are very porous. So a good analogy would be take a teaspoon of one of the best sorbing metal organic frameworks, and it has a surface area of a football field. And
really?
It's because
That's
of that
extraordinary.
and it's because of that very high surface area that these materials are ones that can store a lot of molecules. Those molecules could be out of gases, or it could be out of liquid, or you could install catalytic sites and do catalysis. But in the case of direct air capture, what we're talking about really is the ability to process a very large volume of air. And because we design these materials very selectively to capture or interact with particular molecules that are in the air, it means that we can design them such that they're very selective for carbon dioxide, which is a relatively small percentage of by volume of the atmosphere.
So a tremendous number of advantages with that solvent by the sound of it. Can I ask each of you, this is not a technology question, or it's at a very general level it is, but what do you say to people who argue that this technology is too expensive, that direct air capture is too expensive, or that we don't need it because, all our problems can be solved by switching to renewables? And I might come back to you on that one first up, Julian.
Thanks, Mary. Yes, I have heard that question. The answer I give most frequently is direct air capture reminds me of what renewables was like about 25 years ago, particularly with solar, because solar at the time was small scale. It was very expensive, a lot more expensive than the grid. But what brought it down in cost was global deployment and scale manufacture. And we can see direct air capture following the same kind of scale curve that solar did. Solar, over a period of 2 decades, became about 1/10 of the price that it was relative to when it first started entering the Australian grid. And I remember when the New South Wales government first celebrated with one of its renewable bodies here the first megawatt of solar being deployed onto New South Wales roofs, and now we do many multiples of that per day. And the sense that we can do everything with renewables misses the fact that there's always going to be some emissions for which that are hard to abate, for which you can't just switch your energy supply. That's fine for Scope 2 and Scope 1 direct emissions. Yes, companies will find ways of reducing direct emissions, but there'll always be that hard to abate set of emissions for which there's no other answer other than carbon removal. And that's why some very large companies have got behind, for example, the Frontier Buying Group, including Meta and Stripe and Google and others, to say, right, if we need direct air capture, if we need carbon removal at scale in a few decades from now to get to 2050 net zero, to stabilize the climate, we actually need to be bringing it through now, even though it's small scale, and yes, it's expensive now, but we need to have it start on that journey, because if we don't start on that journey, we'll never get to the point where we can deploy it by the gigaton in 2 or 3 decades from now. So it's very necessary to have it as part of any net zero strategy.
Deanna, can I come back to you with that same question? What do you say to people who argue that it's all too expensive and that we don't need it because, all we need is renewables?
Well, I guess there's 2 parts to that. The first is about the expense, and the second is whether direct air capture is part of the portfolio of solutions for the world's hopefully zero emissions future, and ultimately for the sustainability of the human race and this planet. So the first question, yes, of course it's expensive. It's a technology and it's relatively new. And there's, as Julian said, there were some early entries to the market by funders such as Frontier, but in many countries of the world, like Australia, there really aren't many support mechanisms for developing technologies like direct air capture and helping to come down the cost curve. But the world has done this. And as Julian said, I mean, I absolutely echo his comments on how, we've seen the evolution of the solar industry, and there are developmental stages that are required for a technology to traverse that trend line, such that the technology becomes cheaper, which direct air capture, if it scales and if it can exploit economies of scale, then of course, it's going to come down the cost curve. I guess the second part of that is, do we need it? Or would it be better, are we delaying the inevitable? We must just, transition fully to renewables. Well, the answer there is really in the word transition. In my eyes, this is a transition, and you can't just flick a switch and expect it's going to happen overnight. And the reality is we do have hard to abate sectors, and the evidence-based analysis by the Intergovernmental Panel on Climate Change, which brings together the world's very best scientists on this problem, demonstrates that unfortunately just adapting and mitigating isn't going to be enough for the world, and we do genuinely need to integrate removals into that portfolio of solutions for moving the world toward a more sustainable and resilient future.
Thanks for that. My next question, I'll be interested to see if you both come up with a similar time frame. I'm wondering what you each think is an ambitious but achievable timeline for bringing direct air capture into the mix as a significant part of Australia's efforts to fight climate change. Deanna, first up.
Well, as a scientist, I always look to the evidence, I'm afraid. So I look here to some recent analysis by the Climate Change Authority, and in their analysis of various modelling that's been done, they suggest that here in Australia by 2035, that direct air capture will be entering the mix, the portfolio of options that we need for adaptation, mitigation, and removals, and we need all of them together as a suite of solutions to be able to move toward our net zero targets. So we are going to need it, but again, it's not going to be overnight, because at the moment we don't have the scaling of direct air capture, and of course, as we were just talking about, there's still the expense of direct air capture.
Yep. Okay. So 2035, that's 10 years away. So, no pressure. It doesn't give you long. Julian, is that the sort of same sort of timeline that you think is ambitious but achievable?
Yes, I think it depends on when we say, okay, when does it make a significant impact? It's all around that word of significant, how you define it in the scale of global ambition and Australian impact. So 2035 actually to me seems like a long way away, 10 years. I'm actually focused on making a start, because we can't get it to a meaningful position until we've actually made a start. So for us, it's all about getting the first project up and running that we're hoping to do next year in 2026. And then from there, we've got a demonstration project that we can then build on and say, okay, you've seen it run, now let's build a bigger scale direct air capture project. And that's following a similar trajectory to say what Climeworks has done in the Northern Hemisphere, starting with a 1 or 3 tonne per day demonstrator, feeding a greenhouse, and then building a 4,000 tonne per year plant, and now building a 9 times that in Iceland. So the pathways are there for us to show how we can use modular direct air capture to do scale up and to add a multiple of scale each time we do a new project. The other way of doing it.
Yeah.
Oh, sorry, go on.
Oh, I was just wondering, could you give me some figures on the volume? So the first up, the demo plant, and then...
Well, our first project is planning for 1 tonne a day, which is about 300 tonnes per year. which is a demonstration project. But then our first commercial project would be similar scale as the Climeworks project, so 4,000, 5,000 tonnes per year. Then the next one that they're building is 9 times that, so 36,000 tonnes per year. And the other way of doing it is just thinking big to start with. And so Carbon Engineering, which is now being purchased by Occidental Petroleum, they're building straight off the bat 500,000 tonnes per year in America. So that's a very big, and that will be the biggest direct air capture project up and running in the world. And that's planned to be commissioned this year. So there is a lot of investment going into it. And as I said, a few different ways of thinking about scaling. What we like about doing it small scale is very similar to solar. You can innovate without spending billions each time you build a new project, because especially working with metal organic frameworks, you can test them at the lab scale, then you can test them at prototype scale. And once you know that it's got the performance characteristics that you need, you can then deploy it into a range of machines.
Okay, so you obviously want to increase the size of these things as quickly as possible, as quickly as feasible, and it is a modular system. How many facilities would be needed for direct air capture to play a substantial role in Australia? And are there any constraints on where they need to be located?
I go back to the CCA modelling that Deanna mentioned. We really want to be in the megaton scale by the middle of the next decade. And so the constraints are really on the technological scale up, obviously, which is all on our side. And then obviously the geological storage to take the CO2. On that part, I'm less concerned about constraints, because Australia is actually quite ideally suited to solar powered direct air capture, because we've got a large availability of land. We've got, in most places, an excellent solar resource. And we have a number of CCS projects that are up and running, carbon capture and storage projects. And direct air capture can link in with existing carbon capture storage projects to then effectively combine the CO2 and store it together. If you were looking for a geological storage project that only took the output from a DAC field at small scale, that would be a lot harder to justify economically. So our strategy is to partner with existing or future developments of storage resources. And Australia is quite well endowed with a number of very large potential storage resources that can take CO2. And obviously the direct air capture is just the first part of it. You don't create a carbon removal project unless you're physically removing CO2 molecules from the air and taking them away from the atmosphere, which in our case means geologically sequestering them.
Okay, so it would be a supplement to CCS projects that are either operating or planned. Is that correct?
Correct. That's right.
Yeah. So in terms of the phase up, meeting that 2035 deadline or that time frame that the Climate Change Authority thinks is feasible, Deanna, on the sorbent side, how long do you think it's going to take before you're going to be on the phone to direct air capture companies saying, we've got the perfect sorbent, or we've got the one that we're completely confident is going to work best, and now it's time for you guys to just start building these things quick, smart?
Well, as Julian said, we're already well on the way. So actually there's, Julian can probably explain very well a little bit more here, but actually we're already on the second prototype. As Julian says, these are modular, so they're actually already at scale. There is no more scaling to be done. So in fact, we are already working at the scale. Obviously, there's a second scaling, which is to do then with the scaling of the number of units, obviously, but we are already producing the material, and it is already being integrated into the direct air capture modular system of AspiraDAC. And as Julian said, it is already cycling. So that work is well underway.
And where do we get these? I mean, this is a stupid question, I guess, but how do you get a metal organic framework? How do you actually create these sorbents? And which country do you get them from? Do we make them here, or do you have to import them? How does it work?
Yeah, so look, we do make it here, and we have, and in working together with a number of direct air capture companies such as AspiraDAC and Southern Green Gas over the last 6 years or so, we really have prioritised the use of green and sustainable chemical approaches to making the materials. We've also thought very carefully about sourcing of the raw products, and we've obviously heard a lot about the critical minerals challenges for the world. Yeah. And so Australia being obviously a key producer of those critical minerals, we have focused on the raw materials being provided by Australia, or where we're able to ensure that we know the origin and that obviously it complies with our core concerns around it being ethically sourced and sustainably sourced. So all of that comes into our thinking around not just the making of the material itself, but also making sure that and thinking ahead to the large-scale scaling of the material synthesis, that we're ensuring that right from the very get-go, we're designing for a sustainable process.
Yeah, okay. And are they costly? Do they cost a lot, these materials?
Look, some do. It depends on what the metal is and what the organic bit is that makes up the metal organic framework, and then, of course, any instrumentation that's required for the synthesis of the material. And as you'd expect, over the years that we've worked together with industry partners, we've obviously done techno-economic modelling, and we've sought to really bring the cost of the material down, because it is a substantial fraction of the overall cost of the direct air capture system itself. But in doing that, what we've been able to discover is that we can use alternate synthesis methods in some cases that in fact don't require, any medium at all to make the metal organic framework. So I think actually the, that push to make the material more economically has actually also pushed innovation. And I think that's, speaks right to the heart of why it's so crucial for industry and academia to work together, because both drive innovation in one another.
I hope you're enjoying the chat so far. Just a reminder that Track Changes is a labour of love at the moment. If you're interested in sponsoring some episodes, you can contact me at murray@earthed.au. Okay, back we go to hear more about DAC. Julian, coming back to you, there has been talk of Australia importing carbon dioxide for sequestration. Does direct air capture mean that the transport of CO2 is pointless? I mean, is it actually going to be cheaper to use direct air capture technology for large emitters, maybe in Japan or Korea, to sign a contract with say AspiraDAC or to capture CO2? Is that going to be cheaper, do you think, than it is for them to ship it here for disposal?
It's a very interesting question, Murray. And I've always thought that given that the planet mixes and moves carbon dioxide around the atmosphere for free, the idea of putting it in a boat on one side of the planet to ship it to another side of the planet for storage has always perplexed me as an economic case, given that with direct air capture, you can capture it from anywhere on the planet. And with solar power direct air capture, you're effectively bringing the energy supply for the direct air capture project with you, so you can co-locate with the storage resource. So the whole idea of what we're doing is to actually minimize any kind of cost of carbon dioxide transport. And also, when you think, it's not just the carbon dioxide transport, it's also the fact that it would have had to be captured somewhere anyway, say in Japan or Korea. So, and the capture of it comes with a cost as well. So if you're going to capture it and transport it, we've always thought that it probably makes more sense just to capture it where you want to store it. Maybe because the direct air capture is not yet at scale, but boats to transport liquefied, whether it's LNG or liquefied other elements, maybe people have thought, well, we can put it in a boat, we can design a boat, and that's at scale. And then there are projects being developed to do just that here in Australia. Maybe it's the fact that those techniques might be seen as at scale now. But down the track, once the direct air capture is economic, I would see it as I said, a very economically challenging feasibility study to put up relative to just have a contract to capture and store at the source where you would store.
I mean, intuitively, it does seem like it would have to be cheaper, or at least no more expensive. But I mean, do you have a whole lot of Japanese and Korean companies, big emitters, beating a path to your door, or you can see them there just waiting in the wings, seeing how things pan out?
It's interesting to see how large emitters are looking at this equation, and I mean, Japan's very serious about decarbonisation and net zero, and they are looking at a whole range of different things at scale, a whole range of different ways of decarbonising, and direct air capture is one of them. In terms of buying pressure, most of the buying pressure we're seeing is from actually large American corporates with very strong balance sheets, and maybe it needs to be said, relatively low emission profiles. So I'm thinking of companies like Stripe and Microsoft and so on that can afford to back a new technology like direct air capture. So they are the main buyers that we've seen in the market for carbon removal, and it is actually a voluntary, as we've said before, a voluntary carbon market purchase to go and buy carbon removal. So it's a very interesting market, and we're very very invested in watching this market evolve.
Okay, well, let's keep talking about finance, since you brought up the topic, because it's great to have some money up front, I guess, from Meta and the other big tech companies. But well, we have other schemes. We have the ACCU scheme. There's various crediting schemes. There's a whole range of market mechanisms, which of course you'd be very familiar with in your corporate carbon role. But so I'm just wondering about the potential to use those sorts of systems. I mean, what you would like to see in terms of the adaptation of those systems to help facilitate the development of this technology.
Yeah, so we've seen the voluntary carbon market be the main mechanism for pulling through direct air capture from those large global corporates that I've mentioned before. And it's very analogous to a renewables project, whereby if you're building a wind farm, you want to sell a forward offtake agreement for the renewable certificates. We are aiming to do the same thing with offtake agreements for carbon removal. And as you mentioned, we've sold 500 tonnes to Frontier, and that was as an advanced market commitment. And we need to secure effectively the rest of the book, the forward book, to help us get to a final investment decision on the project. So offtake is the critical thing for us. There are different approaches to subsidy support. The US, at least until recently, was supporting direct air capture through the Inflation Reduction Act. We're just, along with the rest of the industry, seeing where that all goes now under the new administration. But in Australia, we haven't had that kind of mechanism, but obviously there's the ACU scheme that at the moment doesn't pull through and doesn't include DAC or carbon removal or any kind of pull through of those kind of technologies because it was very focused, as we said before, on nature-based solutions. So regardless of what the mechanism is, because it is expensive technology and expensive carbon credits, the key really is finding customers and investors that are interested in seeing this technology get to the next scale.
Okay, but I don't want to go too far into the weeds on this, but say, for example, to benefit under the ACU scheme, is it the case that all you need is a method, or would there need to be legislative changes? And what about safeguard mechanism credits?
Well, the method, in effect, is a legislative piece. It has been raised as an issue: can direct air capture be included in, or can carbon capture and storage be included in the ACU scheme? The issue has always been about accounting. How do you account for direct air capture that takes place in Australia, but it doesn't feature in any of the traditional categories of emission accounting for the country? Because it's not an emission reduction, because we're not actually we're not reducing in an existing emission. And it's not nature-based because it doesn't involve forestry or any other agricultural mechanism. So it hasn't found a place in the accounts that can then allow the government to understand how it then adjusts its the Australian greenhouse emissions accounting. So it's got some regulatory issues to sort out if it was to do that. But I've always thought that at least from a AspiraDAC perspective, it would actually take a lot of time and regulatory effort to include it under the ACU scheme or the safeguard scheme. Our focus has really been on finding the customers that are interested in pulling it through. And obviously, having an ACU, if it was an ACU at the same price as all of the nature-based solutions pricing, then it wouldn't really be that much help, because we need that premium price that we're seeing in the voluntary carbon market.
Yeah. Okay. Deanna, are there finance issues associated with the R&D side? I mean, is it something that where you have to spend a lot of time scratching around for funding, or is that are you seeing a lot of money coming in, I guess, for that essential R&D work that you're doing?
I mean, it really depends what country you're in, Murray, and I think things are changing and have changed since Donald Trump's inauguration as well, even for the United States, where previously in late 2023, President Biden or ex-President Biden had introduced a $3.5 billion incentive for R&D and direct air capture. So at the moment in Australia, as Julian said, it's not recognised under the current schemes, and so we have found that there are relatively few people, first of all, who understand the R&D needs of direct air capture, and secondly, it really has fallen to very early stage startups to fund the R&D efforts, because there are relatively few other ways. And I think the other complication I'd just throw in is that there is somewhat of a politically charged nature to discussions around direct air capture, and that's important. That we have to be open about those conversations, but it's also important to have the frank discussion around it being an important reality that we will need. And so given, particularly in Australia, the relatively low amount of R&D funding in any case, Australia is one of the lowest of the OECD countries in terms of the reinvestment of GDP. It's about 1.6% versus an international average of somewhere around 3%, which means in general R&D is not well supported at all in Australia, and it's the reason we see a lot of Australian innovations and Australian brain power moving overseas. So I think, as Julian mentioned, just to circle back around, there is an enormous unique value proposition here for Australia. Alongside that, we have our partners in the Asia Pacific region who are looking to us, just being in Japan last week and the reality of listening to them speak about their challenge of having to import 90% of their energy. They're looking to us to help them with that challenge.
Yeah. Okay. And legislation and policy, is there anything on that side that needs to be done? Are you sort of comfortable? I guess it's mostly a question for you, Julian. Are you comfortable that we have the right bits of legislation and policy in place to facilitate this, and there's not regulatory hurdles?
If we just put to one side the financial side of things, I think the regulation policy settings are actually quite supportive for the storage part of it, for sequestering CO2. So that part of it is, I think, conducive to future carbon removal projects. The technology part of it, as Deanna said, it's really just about R&D, and with a focus on the D, the demonstration and bringing things into market. And it should be said that both state and federal governments do have programs for supporting R&D, and also specifically in clean tech and carbon innovation. So I think it's fair to say that, it would be great if there was more support available, but we understand that the energy transition and the green transition more broadly it's a multi-decade, multifaceted journey, and it can't just be on the account of government and taxpayers to fund all of that. There needs to be obviously a mix of a range of different funding mechanisms to make it work. One thing I wanted to mention was the opportunity here. So you've probably heard the phrase renewable energy superpower, and the ability for Australia to use its vast land area and vast potential for renewables. Normally, when you hear that phrase, I think you think about things like green hydrogen, future-facing minerals, potentially sustainable aviation fuel, and those kind of things. I think what direct air capture, and in particular solar-powered or wind-powered direct air capture, opens up is the idea of turning renewable energy through this technology into a whole new export product, being carbon removal. So it doesn't have to be that we're putting things on a boat to export them. The thing about the carbon removal market is you can do it anywhere on the planet, and you can sell to anyone on the planet, and you're providing a service that facilitates net zero. So I'm quite attracted to the concept of the renewable energy superpower concept having another arm to it, which is, let's use this renewable energy to create a whole new export market in carbon removal.
And that is a wonderful concept, Julian. It is a very exciting idea, and I particularly like the idea of having this fantastic new export industry where nothing actually crosses anybody's borders. But so it is a wonderful idea, and hopefully it will come to fruition. My last question now, and it's not about direct air capture. What fact do you wish was more widely known, because knowing it would encourage us or equip us to more rapidly shift to a cleaner, greener economy? Deanna, first up.
That's a hard one, Marie. I think the reality that there is no silver bullet, And maybe here it's not anything complex. It's actually very simple, although we all know that it's more simply said than done. But really that we will need a portfolio of solutions, and that alongside adapting to the changes that are already happening globally, and working as hard as possible to mitigate those emissions during this time of transition, but also in the sectors that are very hard to abate, like agriculture, that we are also going to require carbon removals as well. And no one of those things is going to solve the challenge that's upon us, that was begun, at the start of the industrial age. And it's only going to be through a partnership, really, between all of different sectors, and recognising that actually we're going to need this portfolio of solutions, and being pragmatic about that. I think that's probably just a very maybe simple hope that I have.
That is a great answer. Thanks very much. And Julian?
Similar theme, Murray, as to what Deanna just said. I would hope that it's a very simple message falling out of the most recent IPCC assessment report, that we need carbon removal to get to net zero by 2050. We need 5 to 10 gigatons of carbon removal. But quite often it's a struggle to make that understood, to make it's a simple message, but for people to understand that the getting to net zero is not, you can't do it just by switching to renewables. If only it was that simple. But that sorting scope 2, which is switching electricity supply renewables, is obviously a big part of the conversation. And the green energy transition in Australia is mainly a conversation about the grid and how we switch it to renewables. But when you go offshore, especially to America, the conversation is, yes, there's a lot of focus on that, but also on carbon removal. So that would be my, and I know that Deanna, as part of the Net Zero Initiative, and myself and a whole range of other voices there are working on getting that message out so that it's understood what's actually required to get to net zero.
Terrific. That's another great answer. Thanks very much to you both. It's been a really fascinating chat. I've really enjoyed it and learned a lot. So yeah, good luck to you both.
Thanks, Murray.
Thanks, Murray.
Fantastic.
Thanks for listening. I hope you've enjoyed this episode. If you have, please rate it and share it to help get the word out about track changes. See you next time.